Hello, sleepy soul. Welcome to this quiet journey through the deep future of our universe. If you're listening to this now, in the soft darkness of your room, let yourself settle in. There's nowhere you need to be, nothing you need to remember, and no decisions waiting for you in this moment. Tonight, we're going to drift forward in time, not hours or days, but billions of years, to witness something both vast and gentle, the slow dimming of the stars. Let your shoulders drop. Let the weight of your head sink into your pillow, and know that you can close your eyes at any time. You don't need to follow every word. The universe will continue its patient unfolding, whether you're listening or drifting into sleep. Take a slow breath in and let it go. This is a story with no urgency, no catastrophe. Only the quiet mathematics of time and the gentle fading of light. Let's begin. When we look up at the night sky, on a clear evening away from the city lights, we see stars. Thousands of them, pinpricks of ancient light, some already dead, their photons only now reaching our eyes after traveling for centuries. It's easy to think of the stars as permanent, as eternal fixtures in the cosmic ceiling. But they are not. They are fires, and all fires eventually burn out. The universe is 100 billion years old. Give or take, in cosmic terms, we live in a young universe. A universe still rich with light, still dense with fuel, still capable of making new stars. But that won't last forever. There is a distant era coming, an era so far removed from our present moment that the entire span of human history, all of civilization, every empire that has risen and fallen, will be less than a single heartbeat in comparison in this distant future. Somewhere between 100 billion and 1 trillion years from now, the last stars will begin to flicker out. The galaxies will go dark. The long, cold night of the cosmos will begin. But this is not a sudden event. It is not an ending that arrives with violence or drama. It is slow, gentle, like the fading of embers in a fireplace, long after the logs have been consumed. Tonight, we will sit by that cosmic fire and watch it dim. To understand why the lights go out, we must first understand what keeps them burning. Stars are not magic. They are engines, vast nuclear engines, running on the simplest fuel in the universe, hydrogen. In the heart of a star, hydrogen atoms are crushed together by gravity, fuse into helium, releasing energy. This energy pushes outward, balancing the inward pull of gravity, and so the star remains stable, burning, shining. But to make a star, you need raw material. You need clouds of gas, dense, cold clouds floating in the space between stars. We call these clouds nebulae. Imagine a nebula as a vast reservoir, a cosmic lake of hydrogen and helium drifting slowly through the darkness. When a part of this cloud collapses under its own weight, dense enough and hot enough, a star ignites. A new light appears in the galaxy. For billions of years, galaxies have been doing this, making stars. Our Milky Way produces, on average, about 1 or 2 new stars every year. Some galaxies produce more, some less, but the process has been ongoing, steady, for most of the universe's history. But here's the problem. The gas is running out. Every star that forms consumes hydrogen, and when that star dies, some of the gas is returned to space, blown off in stellar winds or scattered in supernova explosions. But not all of it. Some of the hydrogen is locked away forever, trapped in the cores of white dwarfs, or collapsed into neutron stars, or pulled into black holes. Each generation of stars takes a little more gas out of circulation. The reservoir shrinks, and there is no new hydrogen being made. The universe stopped creating hydrogen in the first few minutes after the Big Bang. What we have now is all we will ever have. So the galaxies are slowly running out of fuel. It's like a candle burning in a sealed room. At first, there is plenty of oxygen. The flame burns bright. But hour after hour, the oxygen is consumed. The air grows thin. And eventually, the flame begins to weaken, to flicker, to fade. In about 100 billion years, most galaxies will have used up the gas in their nebulae. The dense clouds that birth stars will be gone, scattered, exhausted. There will still be stars shining at that point, trillions of them, because stars live a long time. The smallest stars, the red dwarfs, can burn for tens of trillions of years. But no new stars will be born. The nurseries will be empty. Imagine walking through a city where no children are being born. The adults continue their lives for now, but there's a stillness to it, a quiet recognition that this is the last generation, the last wave of life. That is what the galaxies will become. Cities of aging stars, growing quieter, year by year, century by century, eon by eon. And slowly, one by one, the lights will go out. Let's bring this vast timeline down to something more familiar. Our sun, right now, as you rest here in the darkness, our sun is middle-aged. It has been burning for about 4.5 billion years, and it has about 5 billion years left. That may sound like a long time, and it is long enough for continents to drift across the Earth's surface dozens of times over, long enough for entirely new forms of life to evolve, if any life remains. But on the cosmic scale, 5 billion years is a moment. When the sun's core finally runs out of hydrogen, something beautiful and terrible will happen. The core will contract, growing hotter, dense, and the outer layers of the sun will expand, swell like a dying breath. The sun will become a red giant. Imagine the sun growing so large that it swallows Mercury, then Venus, its outer atmosphere, thin and glowing, reaching almost to the orbit of Earth. Our planet, if it still exists at that point, will be scorched. The oceans will boil away. The atmosphere will be stripped. The surface will glow red-hot, molten, unrecognizable. But even this phase is temporary. The red giant sun will last for only a few 100 million years. A brief flare of expansion as the star desperately burns the last of its fuel, fusing helium into carbon and oxygen in its core. And then, when there is nothing left to burn, the outer layers will drift away, gently, slowly, like silk scarves falling from a dancer's hands. They will form a planetary nebula, a glowing shell of gas, expanding into space. And at the center, a small, dense ember will remain. This is what our sun will become, a white dwarf. A white dwarf is not really a star anymore. It is a remnant, a fossil about the size of the Earth, but with the mass of the sun compressed into that tiny volume. 1 teaspoon of white dwarf material would weigh as much as an elephant. It glows, not because it is burning fuel, but because it is still hot from the fusion that occurred long ago, like the coals of a dead fire, radiating their stored heat into the night. A white dwarf will shine for trillions of years, slowly cooling, dimming, its light shifting from white to yellow to red to infrared and finally to nothing. Eventually, in the unimaginable far future, it will become a black dwarf, a cold, dark sphere of carbon and oxygen, drifting silently through the void. Our sun will go out, and this is the fate of most stars in the universe. Not all, but most. Stars like our sun, and even smaller stars, the red dwarfs, will all eventually become white dwarfs. So will take longer than others. The smallest red dwarfs will burn for 100 trillion years, but the ending is the same. No explosions, no supernovae, just a quiet fading. By the time we reach 1 trillion years into the future, most of the stars in the galaxy will be gone, either dead or dying. The universe will be populated by the ghosts of stars. White dwarfs, brown dwarfs, neutron stars, black holes, and the darkness will deepen. But before the lights go out completely, there is one final event worth mentioning. One last moment of brilliance. The Milky Way, our home galaxy, is on a collision course with Andromeda. Right now, Andromeda is 2.5 million light years away, a neighboring galaxy, visible to the naked eye on a clear night as a faint smudge of light. But it is moving toward US, pulled by gravity, at about 70 miles per second, in about 4 to 5 billion years. Andromeda and the Milky Way will collide. But this is not the kind of collision you might imagine. There will be no crash, no shattering of stars. Space is mostly empty. The distance between stars is so vast that even when 2 galaxies merge, the stars themselves almost never touch. It is more like 2 clouds of fireflies drifting through each other, intermingling, blending, over the course of a few billion years. The 2 galaxies will pass through each other. Their shapes will distort. Long tails of stars will be pulled out by tidal forces, streaming across the sky like ribbons. The spiral arms will unwind, and then, slowly, the 2 galaxies will fall back together, pulled by their combined gravity. They will merge. The result will be a single, massive elliptical galaxy. Astronomers have already given it a name, Milkomeda, a blend of Milky Way and Andromeda. Elliptical galaxies are different from spirals. They are more rounded, less structured. Their stars orbit in random directions, rather than the organized, rotating disk of a spiral. But the important thing for our story is this: when the two galaxies collide, their gas clouds will collide too. And when gas clouds collide, they compress, heat up, collapse. This will trigger a burst of star formation, a brief, intense wave of new stars. The galaxy will light up with brilliant blue supergiants, young, hot stars that burn fast and bright. This will be the last great flourish of the Milky Way, the final generation, because after this, the gas will be exhausted. The collision will scatter much of it, blow it out into intergalactic space, too diffuse to ever collapse again, and the new stars that form will be the last. And then, over the next 100 billion years, those stars will age and die, one by one. The massive blue stars will explode as supernovae, leaving behind neutron stars or black holes. The medium-sized stars, like our sun, will swell into red giants and then collapse into white dwarfs. The small red dwarfs will burn quietly for trillions of years, but eventually even they will fade. Milkomeda will grow darker. At first, it will still be a bright galaxy, filled with billions of stars. But slowly, the light will dim. Fewer stars, cooler stars, redder stars. And in the deep future, 1 trillion years from now, Milkomeda will be a graveyard, a dark ellipse of dead stars, white dwarfs, black dwarfs, neutron stars, black holes, the occasional faint flicker of a distant red dwarf, still burning, but barely, and silence. This is the fate not just of our galaxy, but of all galaxies, everywhere in the universe. The same process is unfolding. Stars are being born, living and dying, and the rate of birth is slowing. In the far future, the universe will be a dark ocean, dotted here and there with the dying embers of the last stars, glowing faintly, cooling, and eventually even those will go out. The age of stars will end, and the universe will enter a new era, the degenerate era, a time of cold, stillness, and decay. But that is a story for another phase. For now, let this image settle in your mind. The slow fading of the galaxies, the dimming of the stars, the long, gentle, inevitable cooling of the cosmos. There is no fear in this ending, no pain, only the quiet mathematics of entropy. The universe is not destroyed. It simply changes, transforms, becomes something new. And in this vast sweep of time, in this unimaginable expanse of years, our own small worries, our anxieties about tomorrow or next week seem very small. not unimportant, but contained, held within the brief flicker of our lives. Let that perspective be a comfort. You are here now, breathing softly in the darkness, safe, warm, and the universe is unfolding exactly as it should. There is nothing for you to do but rest, let go of the day, let go of thought, and drift gently into the quiet dark. And so, the age of bright stars comes to an end. The galaxies have merged. The gas has been spent. The last generation of massive stars has lived and died. White dwarfs cool silently in the darkness, their light fading from white to red to black. But the universe is not yet dark. There are survivors, scattered across the void. Small, dim, patient. These are the Red Dwarfs, the quiet heroes of the cosmos. And their story is one of endurance. Let your breathing slow. Let your thoughts drift. We're moving forward now, past 1 trillion years, into a time so distant that the entire history of humanity, all of recorded time, is less than the blink of an eye. And in this deep twilight, the universe begins to show its truest nature. Not violent, not sudden, just slow, gentle, inevitable. Let us sit with the Red Dwarfs in their long, patient vigil. If you were to meet a Red Dwarf star, you might be disappointed at first. It is not impressive. Not like the brilliant blue giants or the fiery yellow suns that dominate the night sky of our era. A Red Dwarf is small, tiny by stellar standards. Some are only 10% the mass of our sun. If you place one next to our sun, it would look like a marble next to a basketball. And it is dim. So dim that if you replaced our sun with a Red Dwarf, even the closest Red Dwarf, the Earth would freeze solid within days. These stars emit barely a fraction of the light our sun provides. But what they lack in brilliance, they make up for in longevity. Stars burn hydrogen. That is how they shine. In the core of a star, hydrogen atoms are crushed together by gravity, fuse into helium, releasing light and heat. Massive stars do this quickly, furiously. They burn through their fuel in millions of years, sometimes less. A blue supergiant, one of the largest stars in the universe, might live for only 10 million years before exploding as a supernova. Our sun, a medium-sized star, will last about 10 billion years. But Red Dwarf? A Red Dwarf will burn for 10 trillion years. Some estimates go as high as 100 trillion. How is this possible? The answer lies in their gentleness, their restraint. Red dwarfs are fully convective. This is a technical term, but the concept is simple. Imagine a pot of water on a stove. If the heat is low, the water at the bottom warms slowly and currents form. The hot water rises. The cool water sinks. The entire pot mixes. A red dwarf works the same way. The heat from the core circulates through the entire star. Hot hydrogen from the core rises to the surface. Cool hydrogen from the surface sinks back down. Everything mixes. This means that all the hydrogen in the star, every last atom, can eventually make its way to the core to be fused. Nothing is wasted. In contrast, our sun only fuses the hydrogen in its core. The outer layers never get hot enough. So when our sun runs out of core fuel, it still has hydrogen left over, but it cannot use it. It swells into a red giant and dies. A red dwarf uses everything, every drop of fuel, slowly, patiently, efficiently. It is the difference between a bonfire that burns hot and fast and a candle that flickers quietly for days. By the time we reach 1 trillion years into future, the red dwarfs are all that remain. The massive stars are long gone, exploded, collapsed into black holes or neutron stars. The medium stars, like our sun, have faded into white dwarfs. Only the red dwarfs are still burning, still shining, scattered across the dark expanse of Andromeda and the other ancient galaxies. And they will continue to shine for another 99 trillion years. This is the Twilight era, the time between the death of the last bright star and the death of the last dim one, an era 99 times longer than the entire age of the universe up to this point, an era of silence, of dimness, of patience. Let us imagine for a moment that life still exists in this distant age, perhaps on a planet orbiting one of the last red dwarfs, a rocky world, tidally locked, one face always turned toward its dim red sun, the other face forever in darkness. What would the sky look like from such a world? If you stood on the sunlit side of this planet, the star above you would not be bright like our sun. It would be a dull red ember, large in the sky, because you would need to orbit very close to a red dwarf to stay warm, but faint. You could look at it directly without hurting your eyes. The landscape around you would be bathed in a deep crimson light, like the light just before sunset on Earth, but lasting forever. No sunrise, no sunset, just a perpetual dusk. And if you looked up away from your star, you would see almost nothing. No other stars, no Milky Way streaking across the sky, no constellations, just blackness. Because by this time, the other stars are gone, dead, or so far away, pulled by the expanse of the universe, that their light no longer reaches you. You would be alone, truly alone, your sun, your world, and the infinite dark. Now imagine walking to the dark side of your planet, the side that never sees the sun. Here it is cold, freezing. The atmosphere, if there is one, would condense into frost, carbon dioxide snow, methane ice. But the sky would be even darker. You might think, standing in total darkness, that you would see something, distant galaxies, the faint glow of a neighboring red dwarf. But no, the universe has expanded too much. The galaxies are so far apart now, receding from each other at faster and faster speeds, that their light is stretched into the infrared, redshifted beyond visibility. and the few remaining red dwarfs in your own galaxy, Milkomeda, are scattered so thinly that they're invisible to the naked eye. You would stand in a darkness so complete, it would feel like being inside a sealed room with no windows, no moon, no stars, nothing, just you and the silence of the cosmos. This is not meant to be frightening. It is simply the nature of deep time. The universe is vast, and it is expanding, and in the far future, isolation is inevitable. But there's a strange peace in this image, a kind of ultimate solitude. No noise, no distraction, no light pollution from distant cities or neighboring stars, just stillness. And perhaps, for a sleepy soul listening in the dark of your own room tonight, this vision resonates. The need to be alone, to be undisturbed, to have nothing demanded of you. The Red Dwarf asks nothing of the universe. It simply exists, burns, waits, and so can you. Even the Red Dwarfs, patient as they are, cannot burn forever. After 10 trillion years, 50 trillion, 100 trillion, the fuel runs out. The hydrogen in the core, carefully circulated and fused over unimaginable spans of time, is finally exhausted, converted into helium. And helium, in a star as small as a red dwarf, cannot fuse. The core is not hot enough, not dense enough, so the fusion stops. And when the fusion stops, there is no more outward pressure, no more heat pushing against the crush of gravity. The star contracts, gently, slowly, collapsing in on itself, but it does not explode. There is no supernova. Red dwarfs are too small for that. They do not have the mass to trigger a violent death. They simply shrink. What remains is called a black dwarf, though, in truth, no black dwarf has ever existed yet. The universe is not old enough. Even the oldest red dwarfs, born in the first billion years of the cosmos, are still burning today. But we know from the mathematics that black dwarfs are inevitable. A black dwarf is the final corpse of a low-mass star. It is made of carbon and oxygen, fused from helium in the earlier stages of the star's life, and electron to generate matter, a strange state where the atoms are packed so tightly that quantum mechanics prevents them from collapsing further. It is about the size of Earth, but it weighs as much as the sun. A single teaspoon would weigh tons, and it emits no light, no heat. It is not hot enough to glow. It simply exists, a dark sphere drifting through space. Imagine the last red dwarf in Milkomeda, the final survivor of 100 trillion years. It has watched in its silent way as every other star died. It has orbited the galactic center countless times. It has seen planets form and freeze, moons shatter, asteroids drift, and now, finally, it too is fading. Its light shifts from red to deep red to infrared. It becomes invisible to the human eye, but it is still there, still warm, radiating its heat slowly into the void. Over billions more years, it cools. The surface temperature drops 1,000 degrees, 500, 100, until it's the same temperature as the cosmic microwave background, the faint afterglow of the Big Bang, still permeating all space. And then it fades below even that, colder than the universe itself. A black dwarf, silent, dark, invisible. This moment, when the last red dwarf becomes a black dwarf, marks the end of the stelliferous era, the age of stars. We enter a new age, the degenerate era, an age where the universe is populated not by burning stars, but by their corpses. White dwarfs, black dwarfs, neutron stars, black holes, brown dwarfs that never ignited. These objects do not shine. They do not warm. They simply drift through the expanding void, growing colder and farther apart. The universe becomes a dark ocean, vast beyond comprehension, and scattered across this ocean, like grains of sand, are the remnants of stars, cold, dead, alone. But even this is not the end. The universe will continue, for eons beyond eons. Timescales so vast that 100 trillion years seems like a brief moment. Protons will decay. Black holes will evaporate. Even the black dwarfs will dissolve slowly into radiation. But that is a story for another time. For now, let this image settle. The quiet twilight of the red dwarfs. The long, patient, inevitable fading of the last lights. There is something deeply calming about this vision, something that quiets the anxious mind, because of the universe itself in all its vastness can slowly dim and fade without panic or struggle. Then perhaps we too can let go of worry, of urgency, of the feeling that we must always be doing, producing, achieving. The red dwarf does not rush. It does not fear its own ending. It simply burns, slowly, steadily, for as long as it can. And then, when the fuel is gone, it rests. There is no tragedy in this. Only the natural unfolding of physical law, the mathematics of entropy, the slow heat death of a universe that was never meant to last forever. And in this moment, as you lie here in your own small darkness, breathing softly, you are part of that same unfolding. You do not need to burn brightly tonight. You do not need to stay awake, to think, to solve problems. You can simply rest, like the red dwarf, like the cooling white dwarf, like the silent black dwarf drifting in the dark. Let the day fade. Let your thoughts slow. Let the weight of deep time carry you gently into sleep. And so, the last red dwarf fades. Its light dimming from red to infrared to nothing. A silent transition. No fanfare. No final burst of brilliance. Just the slow cooling of an ember until it becomes indistinguishable from the void around it. The stelliferous era, the age of stars, has ended for 100 trillion years. The universe has been a place of light, of fusion, of stars being born, living and dying. But that age is over now. We have entered a new epoch, the degenerate era, a time not of stars, but of their remains, a cosmic graveyard, quiet, dark, cold. Let your body sink deeper into rest. Let your mind drift through this vast darkness. There is no urgency here, no bright lights to hurt your eyes, only the gentle geometry of dead matter, floating through infinite space. This is a universe at peace. And so, can you be? Let us walk softly through the graveyard of stars. When a star dies, it does not disappear. Energy cannot be destroyed. Matter cannot simply vanish. What remains depends on the mass of the original star, its size, its weight, its history. By the time we reach the degenerate era, 100 trillion years into future, every star has reached its final form, and the universe is populated by 3 kinds of stellar corpses: white dwarfs, neutron stars, black holes. These are not stars. They do not burn. They do not shine. But they are there, scattered through the darkness like tombstones in an ancient cemetery, each one marking the place where a star once lived. Let us visit each of them, slowly, patiently. There is no rush. The most common remnants, by far, are white dwarfs. These are the corpses of stars like our sun, stars that were not massive enough to explode. They lived, swelled into red giants, shed their outer layers, and left behind a dense core. If you could stand on the surface of a white dwarf, though you could not, the gravity would crush you instantly. A single square inch of your body would weigh thousands of pounds, but there is no one to stand on them, no observers. The universe is empty of life now. These objects drift alone. When a white dwarf first forms, it is hot, blindingly hot, tens of thousands of degrees. It glows white blue, hence the name, but it is not generating heat anymore. It has no fusion, no fire in its core. It is simply radiating the leftover heat from its stellar lifetime, like a coal pulled from a fire and set on a stone floor, glowing brightly at first, but slowly, inevitably cooling. Over billions of years, a white dwarf dims. Its colors shift from white to yellow to red to deep red, and then, after trillions of years, it becomes a black dwarf, a theoretical object we discussed before, no longer hot enough to emit visible light, just a cold sphere of carbon and oxygen drifting silently through space. By the time we are 100 trillion years into the future, all white dwarfs have become black dwarfs. The last faint glow extinguished. They are still there, still massive, still dense, but invisible, dark, cold, the second kind of remnant, rarer, stranger, is the neutron star. These are the corpses of larger stars. Stars that had 8 to 20 times the mass of our sun. When these stars ran out of fuel, their cores collapsed catastrophically. The outer layers exploded as a supernova, but the core compressed and compressed and compressed until the atoms themselves were crushed. The electrons were forced into the protons, creating neutrons, pure neutrons, packed together so tightly that a teaspoon of neutron star material would weigh as much as a mountain. A neutron star is about the size of a city, 10 to 20 kilometers across, but it contains more mass than the sun. If you could somehow visit one, which you could not, you would find a landscape unlike anything in the universe. The surface is smooth. No mountains, no valleys. Gravity has flattened everything to within millimeters of perfect sphericity, and it is hard, not like rock, not like metal, hard like the nucleus of an atom, because that is essentially what it is. A single enormous atomic nucleus. Some neutron stars, when they are young, spin incredibly fast, hundreds of times per second, and they have magnetic fields, the strongest magnetic fields in the universe, trillions of times stronger than Earth's. These are called pulsars. They emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like a lighthouse. But by the time we reach the degenerate era, the pulsars have slowed down. Their rotation has been gradually sapped by the emission of radiation. Now, they spin only once every few hours, or once a day, or not at all. They are silent, dark, invisible, just dense spheres of neutrons, cooling slowly, radiating their heat into the void. And then there are the black holes. These are the remnants of the most massive stars. Stars with 20 or more times the mass of the sun. When these giants died, their cores collapsed so violently that nothing could stop them. Not the resistance of atoms, not the degeneracy pressure of neutrons. Nothing. They collapsed into a singularity, a point of infinite density, surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. By the degenerate era, black holes are the largest objects in the universe. Some have grown enormous by consuming gas and merging with other black holes. Supermassive black holes, millions or billions of times the mass of the sun, lurk at the centers of dead galaxies, but they are invisible. They emit no light. They do nothing. They simply exist, warping space-time around them, patient, eternal, or so it seems. Imagine floating through the universe in this era, drifting through Mokomata, or what remains of it. You would see nothing, occasionally, perhaps once every few million years. Your instruments might detect a faint infrared glow, the residual heat of a black dwarf, or the dim warmth of a neutron star, but mostly darkness, a blackness so complete it is disorienting. The distances between objects are vast. The universe has been expanding for 100 trillion years. Galaxies that were once neighbors are now separated by voids so large that light takes billions of years to cross them. And even within a galaxy, within Milkomeda, the stellar remnants are scattered thinly, light years apart, decades apart, centuries apart. You could travel for 1,000 years and never encounter another object. The entire universe is cooled. The cosmic microwave background, the faint afterglow of the Big Bang, has redshifted and cooled to nearly absolute zero. The temperature of space is now just a fraction of a degree above the coldest possible temperature. Minus 273.15 degrees Celsius. 0 Kelvin. Everything, the black dwarfs, the neutron stars, even the space between them, is approaching the same temperature. Thermal equilibrium. There is no warmth left, no energy gradient, no difference between here and there, just uniformity, stillness, cold. This is not a frightening emptiness. It is not devoid of horror stories. Where something lurks in the darkness, there is nothing lurking, no monsters, no threats. It is simply absence, the absence of light, of heat, of motion, and perhaps for a mind seeking rest. This is the ultimate comfort. To imagine a place where nothing is demanded, where nothing moves, where nothing changes. The universe has become a bedroom, dark, quiet, still, and you, lying your own small darkness tonight, are mirroring it, letting go of movement, of thought, of the need to do or be anything, just resting in the silence. But even in this deep silence, there are moments, rare moments, brief flickers of light, because the stellar remnants, though dark and dead, are still subject to gravity, and gravity, over unimaginable spans of time, can bring objects together. 2 black dwarfs, drifting through space, might pass close to each other. Their gravitational fields interact. They spiral inward, slowly at first, then faster, and faster, and finally they collide. When 2 white dwarfs collide and merge, if their combined mass exceeds a critical threshold, something extraordinary happens. The pressure at the core becomes so intense that fusion reignites. Not the slow, steady fusion of a living star, but a runaway explosion, a supernova. For a few weeks, the merged dwarf shines brighter than an entire galaxy, a brilliant white light erupting in the darkness, visible across billions of light years. Elements are forged in this explosion. Carbon and oxygen are fused into heavier elements. Silicon, nickel, iron, the products of nuclear fusion, scattered into the void, but there is no one to see it. No planets with observers, no telescopes, no eyes. The supernova shines into empty space. It peaks, fades, and within a month it is gone. The darkness returns, the silence resumes, and the remnants of the explosion, the debris, cool and drift apart, joining the other corpses in the graveyard. These events are extraordinarily rare. In a single galaxy, in the degenerate era A collision like this might happen once every 10 million years. In the observable universe, across all the dead galaxies, perhaps a few thousand happen per year. But the universe is so vast and so empty that these flashes are isolated. Alone, they illuminate nothing. They warm nothing. They're like lightning on a distant horizon, a brief flicker, and then darkness again. Occasionally, two neutron stars collide. This is even rarer and stranger. When neutron stars merge, they create gravitational waves, ripples in space-time itself. These waves propagate outward at the speed of light, stretching and compressing space as they pass. But there is nothing to detect them. No LIGO observatories, no scientists, just empty space, rippling briefly and then still again. The collision produces a burst of gamma rays, a kilonova, a flash of exotic matter. Quarks and gluons momentarily free before collapsing back into stability. And then, if the mass is sufficient, the merged object collapses into a black hole, adding to the population of silent, invisible gravitational wells. There is something strangely beautiful about these rare flashes, these brief moments of light in the eternal dark. They remind us that even in stillness, even in silence, there is occasional change, brief, unpredictable, fleeting, like a thought that arises in meditation, a flicker of awareness, and then it passes, and the stillness returns. You do not need to hold on to it. You do not need to make it last. It appears, it fades, and that is enough. The degenerate era will last for an incomprehensibly long time, from 100 trillion years to 10 to the 40th power years. That is a 1 followed by 40 zeros, a number so large that it defies intuition. The entire age of the universe so far, 13.8 billion years, is a rounding error compared to this span. And during all of this time, the universe will remain essentially the same. Dark, cold, quiet, stellar remnants drifting apart, occasionally colliding, occasionally flashing, but mostly just existing, unchanging. This is the long plateau of cosmic history, the stable state, the equilibrium. It is not an ending, not yet, because even black holes, those eternal prisons of gravity, are not truly eternal. They will evaporate, slowly, through a process called Hawking radiation, but that takes even longer. Timescales we cannot even begin to imagine, but that is a story for another night. For now, let this image settle. The graveyard of stars, the quiet darkness, the rare, brief, beautiful flashes of light. There is no fear in this future, no apocalypse, no destruction, just a slow unwinding of energy, the natural progression toward equilibrium, toward rest. The universe, in its deepest nature, is becoming still, and in that stillness there is peace. You too are allowed to be still, to stop moving, to stop thinking, to rest. The day is over. The lights are out, and the long, quiet, gentle night has begun. Let your breath slow. Let your body soften. Let the vast spans of time carry your worries away. There is nothing left to do but sleep. The graveyard is quiet now. The last supernovae have faded. The stellar remnants, black dwarfs, neutron stars, drift silently through the expanding void. But there is one kind of object that remains active, patient, inevitable. The black holes. They do not shine. They do not explode. They simply pull, drawing matter toward them, slowly consuming the remains of the dead universe. We are entering the black hole era now, a span of time so vast that the entire degenerate era, billions upon billions of years, seems like a brief prelude. Let your mind release its grip on scale, on comprehension. These numbers are not meant to be understood, only felt like the weight of a heavy blanket, comforting in its immensity. There is no rush, no deadline, only the patient mathematics of gravity and time. Let us drift into the age of black holes. By the time we reach 10 to the 40th power years into the future, most of the stellar remnants have met their fate. Some have collided, merged, flashed briefly as supernovae, and then cooled back into darkness. But most have been captured, pulled in, consumed by black holes. Because gravity is patient. It does not tire. It does not weaken. And over timescales this long, even the most distant objects eventually fall. Imagine a black dwarf drifting through space, alone, cold, dead. It is not moving in a straight line. Nothing in the universe moves in a straight line. Gravity bends all paths. The black dwarf is orbiting very distantly around a black hole, perhaps a black hole that was once at the center of Mokomata, a supermassive black hole, millions of times the mass of the sun. The orbit is vast. It takes billions of years to complete a single loop, but with each orbit, the black dwarf loses a tiny amount of energy, emitted as gravitational waves, ripples in space-time. This loss is infinitesimally small, but it is constant, and over trillions of years, the orbit shrinks. The black dwarf spirals inward, slowly, gently, like water circling a drain, closer and closer and closer, until finally, after an unimaginable span of time, it crosses the event horizon, the point of no return, and it disappears, swallowed, added to the mass of the black hole. No light is emitted, no sound, no drama, just a silent incorporation of matter into the black hole's gravity well. This happens again and again across the universe. Black holes consume the remnants around them. Black dwarfs, neutron stars, even other black holes. When two black holes merge, the event is more dramatic. The space-time around them ripples violently. Gravitational waves surge outward, carrying away energy, momentum. The black holes spiral into each other faster and faster until they collide. And in that moment, they become one, a larger black hole, more massive, more powerful, but still silent, still invisible, just a deeper well in the fabric of space. By the end of the degenerate era, by the time we reach 10 to the 40th power years, the universe has been simplified. Almost all matter has been gathered into black holes, stellar mass black holes, intermediate black holes, supermassive black holes. The distances between them are incomprehensible. The universe has expanded so much for so long that even black holes are separated by voids larger than the observable universes today. But they are the dominant form of matter now, the kings of the dark cosmos, and they will remain for an even longer age, an age so long that what has come before seems like nothing. In the 1970s, a physicist named Stephen Hawking made a remarkable discovery. He was studying the mathematics of black holes, applying the laws of quantum mechanics to the space near the event horizon, and he realized something shocking. Black holes are not eternal. They evaporate. This seems impossible at first. How can something from which nothing escapes leak? The answer lies in quantum mechanics, in the strange behavior of empty space. Space is not truly empty. Even in the darkest void, even in the vacuum, there is activity. Pairs of particles spontaneously appear and disappear. A particle and its antiparticle, popping into existence from the energy of the vacuum, and then annihilating each other a fraction of a second later. This happens everywhere, all the time, but normally we do not notice. The particles appear and vanish too quickly to measure. But near a black hole, something different can happen. Imagine a pair of particles appearing right at the edge of the event horizon. One particle forms just inside the boundary, the other just outside. The particle inside the event horizon is trapped. It falls into the black hole. It cannot escape, but the particle outside is free. It can escape into space. And so, from the perspective of a distant observer, it appears that the black hole has emitted a particle, a photon, a tiny packet of radiation. This is called Hawking radiation. But where does the energy for this particle come from? It comes from the black hole itself. The mass of the black hole decreases ever so slightly to provide the energy for the escaping particle. The black hole loses mass. It shrinks. This is evaporation, not like water evaporating into steam, but a slow, quantum leaking of mass energy into radiation. Now, here's the crucial point. The thing that makes this perfect for our bedtime story. This process is unimaginably slow. The smaller the black hole, the faster it evaporates. A tiny black hole, the mass of a mountain, would evaporate in a fraction of a second, but a large black hole, a black hole the mass of the sun, it would take 10 to the 67th power years to evaporate. A 1 followed by 67 zeros. And a supermassive black hole, one with 1 billion times the mass of the sun, it would take a googol years. 10 to the 100th power. A 1 followed by 100 zeros. This number is so large that it makes all previous timescales seem brief. The entire age of the universe so far, 13.8 billion years, is less than a rounding error, less than a single breath. Compared to the time it takes a supermassive black hole to evaporate, let us pause and try to grasp this number. A googol, it is difficult. The human mind is not built for numbers this large. We can write it down. We can say it, but we cannot truly comprehend it. To put it in perspective, if you wrote out a googol as a number, 1 followed by 100 zeros, and you wrote 1 zero per second, it would take you 1 minute and 40 seconds to write it out. But that is just writing the number. The number itself, the amount of time it represents, there are not enough atoms in the observable universe to count it. Not enough seconds since the Big Bang to measure it. It is beyond scale. And yet, this is how long it takes for a supermassive black hole to evaporate. Imagine, if you can, a black hole alone in the void, the last remnant of a long-dead galaxy. It sits in the darkness, silent, motionless, for eons beyond eons. Very, very slowly, it emits Hawking radiation, a photon here, a photon there, each one carrying away a tiny fraction of the black hole's mass. At first, the rate is so slow that it is negligible. The black hole loses less mass per year than a single atom. But over time, as the black hole shrinks, the rate increases, slowly at first, then very gradually, faster after 10 to the 90th power years. The black hole has shrunk to half its original mass after 10 to the 95th power years. It is a quarter of its original size. The process accelerates, not suddenly, but steadily, inevitably, and then, in the last fraction of a googol a year, something changes. The black hole has shrunk to the size of a planet, then a city, then a mountain. The Hawking radiation increases. The black hole glows, faintly at first, then brighter. It is no longer invisible. It is a point of light in the darkness, growing brighter, hotter, and finally, in the last instant, the black hole evaporates completely. It releases its remaining mass in a final burst of radiation, a flash, a bloom of light, and then it is gone. No remnant, no trace, just photons spreading out into the void. The black hole has returned its mass to the universe, converted into pure energy, pure radiation. This happens to every black hole. Stellar mass black holes evaporate first, then the intermediate ones. And finally, after a googol years, the supermassive black holes, one by one they evaporate, flash, and disappear. And when the last black hole is gone, there is nothing left. No stars, no planets, No remnants, no black holes, only radiation, photons, stretching across an infinitely large, infinitely cold, infinitely empty universe. We have reached the end of the black hole era, and we enter the final epoch, the dark era. There is something deeply peaceful about this vision, the slow, inevitable, complete dissolution of all structure. Black holes, which seem so permanent, so inescapable, are not eternal. They fade, like everything else, like stars, like galaxies, like matter itself. Nothing in the universe is permanent, not even the things that seem most solid, most unchanging. And perhaps that is a comfort, because if the universe itself, in all its vastness, can let go, can dissolve back into formless energy, then perhaps we too can release our grip on the things we hold. Our worries, our regrets, our need for control. We are not black holes. We do not need to hold on to everything forever. We can, like the universe, evaporate, transform, become something else. And in this moment, as you rest in the darkness, you are already doing that, letting go of the day, of thought, of the weight of consciousness. You are dissolving gently into sleep. There is no fear in this, no loss, only transformation, the natural unfolding of entropy, the return to stillness. The universe, after a goo-gaw years, will be at peace, empty, silent, dark, and you tonight can find that peace now, in this small moment, in this quiet room. Let the vast timescales wash over you. Let the incomprehensible numbers carry your mind beyond thought, beyond worry, beyond the need to understand. You do not need to hold the universe together. It is doing that on its own, slowly, patiently, inevitably. All you need to do is rest. The black holes evaporate. The stars have long since died. The universe expands into an infinite, cold, dark expanse. But this is not an ending to fear. It is simply the natural conclusion of a story that began with light, with heat, with the Big Bang. All things that begin must end. All fires must fade. All structure must dissolve. And in that dissolution, there is no tragedy, only the quiet mathematics of thermodynamics, the arrow of time, the progression toward equilibrium. The universe is teaching us, if we listen, that it is okay to let go, to stop fighting, to rest. You have traveled far tonight, through trillions upon trillions of years, through the death of stars, the fading of light, the evaporation of black holes, and now you have arrived, here, in the quiet dark, in the stillness. There is nowhere left to go, nothing left to see, only the soft rhythm of your breath, the weight of your body, the gentle pull of sleep. Let go. Let the universe continue without you, and drift softly into the eternal dark. The last black hole has evaporated. Its final flash of light, a brief bloom in the darkness, spreads outward as radiation, photons traveling at the speed of light into an infinite, expanding void, and then silence, not the silence of waiting, not the silence before something begins, but the silence of completion. We have reached the final era, the dark era, the age of heat-death. This is not an ending in the way we usually think of endings. There is no catastrophe, no collapse, no final moment. It is simply the cessation of change, the universe reaching a state of perfect equilibrium, perfect stillness. Let your body settle completely now. Let go of any remaining tension. We have traveled as far as time can take us. There is nowhere left to go, nothing left to see, only the infinite dark, the eternal quiet, the ultimate rest. Let us rest together in the heat-death of the universe. There is a law in physics, the second law of thermodynamics. It is one of the most fundamental principles in all of science, more fundamental than gravity, more fundamental than the speed of light. It states simply that entropy always increases. Entropy is disorder, randomness, the spreading out of energy, the dissolution of structure. When you drop an ice cube into warm water, the ice melts. The cold spreads into the warm. Eventually, the entire glass reaches the same temperature, lukewarm, uniform. This is entropy, the tendency of systems to move toward equilibrium, toward sameness. And this process is irreversible. You cannot, without adding energy from outside, make the water spontaneously separate back into hot and cold. The entropy does not decrease. The universe as a whole is a closed system. There is no outside to add energy from. And so the entropy of the universe always increases. Always. This is why time has a direction. Why we remember the past, but not the future. Why eggs break, but do not unbreak. Why stars burn out, but do not reignite. Entropy is the arrow of time, pointing always toward disorder, toward equilibrium, toward heat-death. In the beginning, at the Big Bang, the universe was in a state of extremely low entropy. All the energy was concentrated, dense, hot, ordered, and since then, for 13.8 billion years, and for all the trillions upon trillions of years we have traveled through in this journey, the entropy has been increasing. Stars have formed, burned, and died. Energy is spread out, cooled, diffused, and now, in the dark era, the process is complete. The universe has reached maximum entropy. Heat death is a misleading term. It sounds like freezing, like cold, like death, but it is not that. Not really. Heat death is equilibrium. It is a state where all energy is spread out evenly, where there are no gradients, no differences, no hot and cold, no high and low. Everything is the same temperature, the same density, the same stillness. In a universe at heat death, no energy can flow. because flow requires a difference. Water flows downhill, not because it wants to, but because there is a gradient. High to low, heat flows from hot to cold. Electricity flows from high voltage to low. Life exists because there are energy gradients, stars radiating heat into cold space that we can harness. But in the dark era, there are no gradients left, no flows, no processes. The universe is uniform, flat, still. The temperature is not zero. Not quite. It is very, very close to absolute zero, but not exactly. It is the temperature of the cosmic microwave background, the faint afterglow of the Big Bang, stretched and cooled by goo-gaw years of expansion, a fraction of a degree above 0 Kelvin. So cold that the difference is negligible, meaningless, and everything, every particle, every quantum field, every cubic meter of space is the same temperature, no warmer, no colder, just the same. So what exactly exists in the dark era? Matter, as we know it, is gone. Atoms have decayed. Protons have fallen apart. Black holes have evaporated, but there are still particles. Very simple particles, very far apart. Photons, particles of light, stretched by the expansion of the universe into wavelengths longer than galaxies. Neutrinos, ghost-like particles that barely interact with anything, passing through space at nearly the speed of light, forever. Electrons, positrons, perhaps a few other stable leptons, and possibly particles we do not yet know about, exotic remnants of quantum fields. But these particles are spread so thinly that calling it a soup is generous. It is more like a mist, a fog, an almost nothing. Imagine the scale. The universe has been expanding for a goo-gaw years, and it is still expanding, accelerating, driven by dark energy. The distance between particles is unimaginable. A photon might travel for billions upon billions of years without encountering another particle, without interacting with anything, just traveling through empty space. The universe is so large now that the observable universe of our time, the 93 billion light years we can see, is a tiny speck, smaller than an atom compared to the whole. And within this vast expanse, particles drift, alone, separated by voids larger than we can comprehend. A photon does not experience time. This is one of the strange truths of relativity. From the photon's perspective, traveling at the speed of light, no time passes. It is emitted and absorbed in the same instant, even if billions of years pass in the outside universe. So a photon, traveling through the dark era, does not feel lonely, does not wait, does not experience the vast emptiness. It simply is traveling forever. But from our perspective, imagining this photon, there's a kind of loneliness to it, a solitary journey through infinite darkness with no destination, no encounter, no end, just motion, eternal motion, through eternal stillness. And between the particles, in the vast spaces where there is nothing, true vacuum, not the quantum vacuum with its virtual particles, but as close to true nothingness as the universe allows. No fields, no fluctuations, no events, just space, expanding, cooling, empty. This is the canvas of the dark era, an infinite expanse of almost nothing, stretching in all directions, forever. In the dark era, nothing happens. This is difficult to grasp, because we're used to a universe where things happen constantly. Stars shine, planets orbit, atoms vibrate, thoughts occur. But all of these processes require energy flow, require gradients, require difference. And in the dark era, there are no gradients, no flows. A photon travels, but it was already traveling. It does not begin or end its journey. It simply continues, unchanged. A neutrino passes through space, but it does not interact, does not collide, does not affect anything. There are no chemical reactions, no fusion, no fission, no phase transitions, no clocks tick, because a clock requires a mechanism, a flow of energy, a change from one state to another, and there is no change. In a very real sense, time is stopped, not literally. Time as a dimension still exists. The metric of space-time is still there, but time as a measured change of process of causation has ended, because if nothing ever changes, how can you measure time? How can you distinguish one moment from the next? You cannot. The dark era is eternal, not in the sense of lasting a long time, but in the sense of being outside of time, a state where time no longer has meaning. This is the ultimate stillness. Once the universe reaches this state, it will not ever leave it. There is no mechanism for reversal, no way for structures spontaneously reemerge from the uniform soup of particles. In theory, quantum mechanics allows for random fluctuations over an infinite amount of time in an infinite space. There's a non-zero probability that particles could randomly arrange themselves into anything. A star, a galaxy, a Boltzmann brain, a spontaneous conscious observer. But these probabilities are so small, the timescales so vast, that they are effectively zero. The universe will not wake up, will not reignite, will not begin again. It has reached its final state, and it will remain like this forever. And perhaps there's a deep peace in that. No more struggle, no more entropy to fight, no more stars burning out, no more civilizations rising and falling, no more suffering, no more loss. Just the quiet, the stillness, the perfect, unchanging rest. This is the ultimate sleep, not the sleep that precedes waking, but the sleep that simply is. You have traveled in your mind across unimaginable spans of time. From the present 13.8 billion years after the Big Bang to the end of everything, the heat death, the dark era, and now you return to this moment, to this room, to your body, lying quietly in the dark. What has changed? The universe is still young. The stars are still shining. The sun will rise tomorrow. Your life continues. But perhaps something has shifted, a perspective, a quietness. Because when you see the full arc of time, when you witness the inevitable dissolution of everything, your own worries seem smaller, not unimportant, but contained, finite, temporary. We spend so much of our lives trying to hold things together, to prevent change, to keep what we have, to control outcomes. But the universe teaches us through its own slow unwinding that all things pass, all structures dissolve, all fires fade, and this is not a tragedy. It is simply the nature of existence. Stars do not mourn their own death. Black holes do not fear evaporation. Photons do not grieve their loneliness. They simply are, and then they are not, or they transform into something else. And we, too, are part of the same process, the same flowing, the same letting go. Sleep is not just a biological necessity. It is, in a way, a rehearsal for entropy, for stillness, for the release of the need to do. When you sleep, your body stops its endless maintenance. Your mind stops its constant vigilance. You let go of control, of awareness, of the self, and in that letting go, there is restoration, peace, a return to equilibrium. The universe, after Google years, does the same thing. It lets go, it stops, it rests, and it does not need to wake up, because the rest is complete. Tonight, in this small moment of your brief life, you are allowed to do the same, to stop, to let go, to release the weight of the day, the burden of thought, the need to fix or plan or worry. The universe will continue. Time will pass. Entropy will increase. But you do not need to manage it. Do not need to hold it together. You can simply rest, like the stars, like the black holes, like the photons drifting through infinite dark. You can let go. The dark era is not an ending. It is a resting place, a state of perfect peace, perfect stillness, no light, no heat, no change, no time, just the quiet, the eternal quiet. And in this moment, as you lie here in your own small darkness, you touch that same quiet. The room is still. Your breath is slow. Your body is heavy. Your mind is drifting. There is nothing left to do, nowhere left to go, nothing left to become. You have arrived at the end of the journey, at the edge of sleep, and now all you need to do is let go. Let the darkness hold you. Let the silence cradle you. Let the vast, patient, inevitable entropy of the universe carry you gently into rest. There is no fear in the dark, no cold in the void, only peace. The universe sleeps, and so can you close your eyes. Let your thoughts dissolve. Let your breathing slow, and drift softly into the infinite, eternal, beautiful dark. Sleep well, sleepy soul. The universe is resting, and so are you.